publishing themselves
Yeah.
or even putting in the chat. So
Yeah.
I did a small research because I think we never met in person. No.
No, I don't think we have a chance to meet in person.
But I don't know. I stalked you a bit, and I saw a few papers on generative quantum generative models, and that you work with Zoe, Holmes, etc.
Yeah.
So I mean, correct me if I'm wrong. I have a small bio of you. You did a PhD in the National University of Singapore.
Yeah.
Cool.
Exactly.
And then a postdoc at Zoe Holmes group in EPFL in Switzerland. Yeah. And now you jump to a faculty member in the Department of Physics in Bangkok.
Chulalongkorn. Yeah.
Cool. That's a super impressive career.
Yeah.
Nice. And well, thank you again for being here with us. And so I don't know if you prepared some slides. Maybe you're super invited to share.
I'm going to share my screen. Let's see if it works. Okay.
Cool.
Okay. People seeing like the entire screen in the presentation mode.
Absolutely. Thank you very much.
Okay.
Super. So the floor is totally yours, and welcome. Thank you very much.
Yeah. Okay. Yeah. Okay. I'm gonna start now then, and thanks for the invitation. And it's like my absolute pleasure to give a talk at your group meeting. So today I'm going to talk about is like quantum machine learning and the journal to its scalability. And but before I started, as Matthias introduced me, right now I'm working in like Chulalongkorn University in Bangkok. So I'd just love to show you a little bit of pictures on what the university and the surrounding area looks like. And it's a bit of an invitation. So if any chance, any one of you happen to love to come and visit or just happen to be nearby and love to come and like look around, just drop me an email. I'm happy to chat and make it happen. Okay. With that saying, so today's talk, we're gonna be divided into two parts. So the first one is the friendly introduction to the quantum machine learning and to this problem of exponential concentration, also known as barren plateaus. And the second part is gonna be this exponential concentration and how it affects different quantum machine learning models, ranging from like supervised learning with parameterized circuit, quantum generative models, to even like a non-parameterized quantum models, like kernel methods or like extreme learning. And as Matthias said, please interrupt me with any questions during my talk. I'm super happy to keep it like very informal. Okay, so let's jump into the first one. I'm going to start like very slowly, and at some point, if it's too slow, just give me a shout. Okay, so of course, we're gonna start with like what is quantum machine learning, and it's as the name suggested, it's just combining two words, right? And it's a fast-growing field, and the main reason why we're interested in this field is we want to achieve some advantage in data analysis and data processing. Okay, but I want to be a bit more like mathematical precise about what I mean when I say like a machine learning model and quantum machine learning. Okay, are you guys also seeing my cursor moving around as well?
Yes.
Okay, amazing. Yeah. Okay, so let me just give you a brief like notation what I mean by machine learning model, right? So the learning model is nothing but a function with some trainable parameters, right? So you have this function f which going to tell you the architecture of your model, and this architecture model gonna depends on some trainable parameters that you're gonna be training during your training process, and then the function is gonna take some input data x. That's like a very generic mathematical description of my learning model. And the most basic model ever imagine it's just like linear regression, right? So you have this one with zeta1 and zeta2 as your parameters, and you just do the linear with the input x. And a bit more advanced is like classical deep neural networks. This one, you just have like a series of linear transformation together with the nonlinear activation functions. And in this case, your parameters are just like weights and biases of your neurons. So far, I haven't added any quantum bit yet, right? So when I'm saying the quantum machine learning, it simply means that some part of my learning model, you have to involve quantum computers in one way or another, right? For example, you might have some parameterized V3, and the basic example that maybe like people here are familiar with is just this, like, you have a data encoding block that you're gonna input some data in, and you just have like a parameterized quantum circuit. Then you interpret the expectation with respect to some observable O as your model prediction. Okay, so that's what I mean by quantum machine learning. And now I'm just gonna briefly cover why we want to build one, right? So to understand that, maybe we're going a bit on the training phase, right? So when we have like classical computer, you build the learning model, it depends on some parameter zeta. Then the training phase is like you have training data, right? You train your parameter, then you have like, once you're done, you have some optimal parameters. Then it's gonna be prediction phase. You're gonna feed in some unseen data, and your model gonna tell, like, for example, it's a picture of cat, and of course there's gonna be some accuracy associated with it. Okay, it's the same thing for quantum one, and so you just replace your classical model, some part of it, with quantum computers. And the main reason why we want to build one is we hope for some advantage, right? For example, you might hope that you can train it with less training data, but at the same time, you can make like a better prediction accuracy, right? And it is like people actually having some theoretical like demonstration on this, right? So there's some proof of principle based on like some cryptographic hardness argument showing exactly this. So great, we have one reason, then let's go, us go and build one, right? What the problem here is that it doesn't simply that easy, right? It's very hard to build a QML model with an advantage, right? Actually, there are many challenges associated to it, right? So for example, this could include like what is a good QML model. It might be as simple as that, or like the what would be the learning problem that is favor for quantum machine learning to do. There's a problem about local minima, and there's a problem about like your comparison to classical ML, right? Because we want to say that our QML works better than classical ML. Hardware noise, classical simulability, but the main one that I want to focus today is the last one, right? It's the exponential concentration, and also known as like barren plateaus. Okay, and the main reason that there are two main reasons why I want to focus on this one. Yes.
Can you please
Sorry.
hide the panel at the bottom?
So, sorry. I think I messed up my slide share screen, and also at the same time, what is the question? Oops. Okay, sorry.
Someone spoke, right?
Yeah, I think someone talked, but I think that might it might be just a noise. Okay, then maybe I keep going.
No.
Yes, Tome.
I was just I was just asking to just hide the panel at the bottom so that the whole screen, I mean, the slide was not completely visible with the slide with the panel at the bottom.
You mean this?
Sorry.
Okay. Now it should be perfect. Cool. Sorry. It's actually one of my rare occasions to use Teams. Okay, but now everything is good. You can now you can see my slide, and there's no like something block the text.
Super good.
Okay, cool. Okay, let's continue then. So we want to talk about this, and that's like main reason why this problem is interesting to talk about. So first is a scalability barrier to QML. So it's the statement about what happened when you actually scale up to large number of qubits. So it tell you a bit about like, not a bit, it tell you a lot about like fundamental limitations of your quantum machine learning. And for the practical reason, it's very easy to come across if you like, if you being agnostic, right? If you being ignorant about how like QML actually works. Okay, but to fully understand that, let me maybe take like a slight detour into like a very closely related subfield of QML, known as like a variational quantum algorithms. And the reason why we look into this field is that the form of the loss function. So in this field, if you see my screen, there are like a big overlaps between the two, right? And in variational quantum algorithms, what you actually doing is you have some kind of like loss function, and then you construct your parameterized circuit, and then you want to minimize this expectation with respect to the observable. Usually your observable define problem that you want to solve, and your u of zeta tell exactly how you want to solve it. And just by looking at the form of the loss function compared to what I showed you previously about like the example of quantum machine learning model, you're gonna see a lot of similarity already, right? It's some kind of like expectation with respect to the observable. And of course, like the two fields are very closely related. So we're gonna talk about exponential concentration problem in this field first as a friendly introduction. And then for the second part of the talk, we're gonna talk about this in the QML. Okay, if you know a bit about how VQA works, it's very similar to how you actually train your QML models, right? You have parameterized quantum circuit, you make some measurement to estimate the loss function, and then this loss function is giving you some like a loss landscape, right? It's the high dimensional surface with respect to your parameters, right? Then you just using your favorite optimization methods on your classical computers to optimize these parameters, and then just keep repeating this process until it converges. And it is susceptible to the same issue about scalability. Okay, and so, and that same issue is the barren plateaus or exponential concentration. So let me first tell you what it is, and then I'm gonna tell you how it can happen, right? So basically, barren plateau is just when you have the loss landscape to be exponentially flat, right? There's a bit of gradients there, but they are exponentially small. So on the left-hand side, you have the landscape with no barren plateaus, just so you can start somewhere and then you go downhill. On the right-hand side, you have the landscape with barren plateaus. It's kind of like exponentially flat. So if you don't get enough precision from your short noise, what you end up doing is you're doing the random walk on this landscape. Okay, so basically, the moral of the story here is that you need exponential resource in order to navigate through this like flat landscape. Okay, mathematically speaking, there are like different ways of defining what barren plateaus actually is. My favorite one is this one. So basically, you have the loss function, and you have mu, which is your concentrated value. This mu is independent of your zeta. So the probabilities over your some like initial parameter distribution. And when you have, so what this equation saying that the deviation from this delta, from this mu by delta is upper bounded by this beta divided by delta square, and this beta is exponentially small. So in other words, the probability of a loss deviating from the mean is exponentially small. When you have like a large number of qubits, this beta become like extremely small, very close to zero, right? So you when you initiate your initial parameter for training over the entire landscape, you're very likely to be on the flat region. Okay, and one way to diagnose it is just to look at the variance of your loss function or the variance with respect to your gradients. And if this one becoming exponentially small, then you know that you kind of like screwed because of this BP effect. And if you look a bit into like the BP papers, you're gonna see a lot about like this variant plot when where you plot the variance of the loss function with respect to the number of qubits, right? So it's going down like that. And when you run your numerics, right, you scale your system a bit, you see whether your model have BP or not. And if you see like it's going down exponentially, then, you know, it's not good.
Supanut, can I interrupt you?
Yes, please.
The typical, like, I don't know, just to mention something, I don't know, McLean's paper, like the Google's paper of 2015, I guess, I don't remember, showcasing like the barren plateau phenomena for one design, two designs, whatever, two designs, I guess. They all these statements and the proof, which is kind of straightforward, is at the level of the gradient of the constants, right?
Mm-hmm.
Is there any super intuitive way to relate like the statements of the gradients with respect to the cost?
Yeah,
I guess,
so it's
like
basically like
or something.
Yeah. So you can imagine like if your gradients. So okay, if I want to talk about barren plateau in the with respect to the gradients, I'm just gonna replacing my L of zeta with the gradients everywhere.
Mm-hmm.
And then it's just basically saying that okay, and in that case also like my mu is going to be 0. So in that case, what it said is that your gradients are vanishing. So you basically your landscape has no gradients, right? It has some gradient, it's just exponentially small. And if you just like, you know, draw a bit, sketch a bit on like a 1D landscape, you're gonna be seeing that, you know, it's like vanishing gradient just imply flat landscape. So that yeah, so I think that the intuitive picture that people should have.
Okay, cool.
Okay, nice. Then let me just like very intuitively tell you also like how we have this exponential concentration. There are a lot of ways. So that's gonna be like a lot of papers behind, but I think like eventually people in the field, they kind of like understand how this concentration coming from, and it's coming from nothing but like curse of dimensionality, aka your objects live in like exponentially large Hilbert space. And the way you see it is just like you rewrite your loss function as like in the vectorization form, right? And you could see that it's basically you compare this like raw object to the O zeta object, and both of them are exponentially large objects. In other words, this is like nothing but inner product between two exponentially large vectors, right? And in general, if you don't handle well these like exponentially large objects, the inner products between them is going to be very close to 0, right? And that is what actually causes exponential concentration. It's basically nothing but like your poor handling of the exponentially large objects. Then what you could ask next is simply like how many different ways I can screw things up, right? How many different ways I can like manage these exponentially large objects, and you're gonna find like all of them, right, leading to exponential concentration, right? So for example, you have the choice of the circuit. If your circuit is too expressive, you're going to have barren plateaus. If your circuit is too entangled, it's going to be barren plateaus again. The target of learning problem also causing this like barren plateau phenomena. The choice of the cost function, noise, of course, noise always kill everything, and so on. So these are some examples. And you might, I might already like overwhelm you a bit, but like let me just like putting things a bit more. So that's also like the link between the absence of barren plateaus and like classical simulation. And also like more and more recently, people start to ask beyond the average over the entire landscape, right? Barren plateau is the statement of the average statement over your loss landscape. But if you think about it, when you do the classical machine learning, people never actually start randomly over the entire loss landscape. You always have like some prior knowledge of how you want to start your training or your optimization. And people looking into like the theoretical guarantees of this like warm start or like over like small angle region of small sub-region of your landscape. And what people found is like if you could somehow manage to initialize close enough to the solution, you could kind of like get away from this like curse of dimensionality. Of course, there's gonna be always some follow-up question. There's always gonna be some subtlety. It's like how close is close enough. We managed to show that it's polynomially close to the solution, but that is pretty small in practice. So that's a lot of open questions into this direction of going beyond average over landscape. Okay, I think by this point, I already overwhelmed you with too much information already. And if you feel like you don't know where to begin, we have some review on this topic of barren plateaus in rational quantum computing. Please feel free to check it out, or drop me an email, send me email asking. We can chat whenever. Okay, so that is hopefully that's the first part. It's a friendly introduction to QML and barren plateaus in the rational quantum algorithms, which is very closely related field to QML. Now I'm going to move into the second part, which is the concentration. Yes.
Can I interrupt you before?
Yeah.
Super cool, like this little small update review on barren plateaus, fascinating. A lot to say, but I'm very interested in this kind of, I don't know how to say it, like assumption, this fact that you pointed in this, say, tale, in which like exponential concentration arises as poorly handling exponentially large objects. Why should this be obvious at all? And then like another question is like, is there any sort of like a discourse of dimensionality arises in classical machine learning, whatever, but exponential concentration or arises, is this like the consequence, or like, why do you say it like is a way of like, no, this is obvious?
Okay, so it's just like, I think basically if you have, so for example, if you do the too expressive, like expressivity induced concentration, basically your model, your model family is just going to be any vectors in your Hilbert space, right? If I have like 2D psi or even like more than that. And basically what you could, the intuitive picture that you could have is just like you pick two random vectors in this large Hilbert space, just like thinking of like just you have two random quantum state, right, in the Hilbert space. The inner product between them is going to be exponentially small. You might say like, yeah, fine, it's the on average the inner product is going to be small, but it's not just that, right? This this concentration happen with the that's another like the variance of this average that happen is also exponentially small. So it's more like whenever I pick two random quantum state, they are going to be exponentially small always. I'm not so sure if that really answer your questions, but that's kind of like the picture that I always have in my mind.
Okay. No, yes, I mean, yes, we have the same picture in this regard, but I was wondering if this sort of notion also applied like in classical contexts.
Yeah,
And there is
yeah,
a lot of
you
like
have,
mapping this.
so that
Sorry.
so okay, so in the review we discuss about this quite lengthily, but what I could like tell you quickly is like the source of that lead to concentration or like this like a vanishing gradients in QML and in like classical ML. They are kind of like different. In QML you have this like exponentially large Hilbert space kind of like built in, right, into your model. So it's like when you just say like you have n qubits, it's already 2 to the n by default, right? In classical machine learning, people show that you have concentration, but not with respect to the number of width, but rather in the number of like depth of your circuit, of your layers. And usually it's just like by doing this like a metric multiplication between two different layers, and if you have the matrix that doesn't respect like a certain property, you could show that, you know, it's going to the signal from early layers is going to dissipate like exponentially with the depth of your network. So it's slightly different. We having the problem with the width, but like in classical ML, you have with the depth. But it's very cool question. Yeah. Yeah, it's the section that we like discuss quite a bit, and then like at some point I think like Gerard really wants to add this one in, and he's like, yeah, I'm gonna write that.
Yes, yes,
Okay,
I remember. Yes, please, sorry to interrupt you. Go on.
Yeah,
I have a question
yes.
about this previous part. So the focus around barren plateaus and this is basically all around the variational part, right? Has there
Yep.
been any research around how does the encoding influence that? Like,
Yep.
could the encoding
Yep.
be kind of a warm start, or I don't know?
Yes. So if about the encoding, like if your question is whether the encoding could lead to concentration as well, that is the last part of the talk.
Okay.
The second one is how the is there a strategy where you use the data encoding to help with circumventing barren plateaus? That's kind of like that actually the very cool question, and we have that in the first part. What we show is like the encoding cannot help getting rid of the BP.
Okay.
But like because it's two different axes, right? You have how do you encode the thing and how you parameterize the thing.
Yeah.
Cool. And but if you have like a smart initialization procedure on this like, you know, parameter angle in the parameter axis, that can help. Yeah.
Cool.
Okay.
Thank you.
I like usually when I give this talk, this like the part where people start to lose some willpower to live on. So, you know, some nice cat to support you. Okay. And yeah, so the second part of the talk is all about like how this knowledge of barren plateaus in VQA generalize to QML setting, right? And like it might seem straightforward, but actually it's not, right? So the QML frameworks are generally more complicated. It usually involve like dataset, nonlinear loss function, and like even some optimization that entirely relying on the classical computers. So you don't have to do this like feedback loop between like quantum and classical like you do in VQA, right? And so yeah, it's not actually straightforward to figure out how things work out. But it's just like to give a little bit of motivation. So you can always see that whenever you do VQAs, you're gonna have this like linear loss, right? Which is the expectation with respect to some observable. And we're gonna be using that quite a bit. Okay, so let's talk about supervised learning with parameterized quantum circuit. And it's just like the brief picture of how you actually train your parameterized circuit in the context of machine learning. As I just said, that here you have some data set. So your data set could be classical data, like actual images of cat and dogs. And if you are in this regime, you need to do some encoding, right? So you could imagine you doing some like CPTP map. I'm being super general here. Like you just have to do some data encoding onto your classical data, and then you have some quantum state that associated with that particular input. Or you could imagine like you are going to the lab, then you cook up some, some experiment on your quantum system, on your quantum hardware, and you just like imagine somehow that you have some quantum data, right? You can somehow use quantum computers to directly manipulate your quantum data. So you can also imagine that this rho of I is already given to you. And then, of course, you're going to have this parameterized quantum channel or quantum neural networks. So here, again, we just consider it as some CPTP map that you parameterize over. And you're going to do some model prediction, which is just expectation of some observable. The framework here that we use is that is in this form, right? There's also some framework that you it's kind of like it's not just with respect to some observable, but I think in the end you need to do some measurement with your quantum computers. Okay, cool. And then you do you have the loss function that you're going to minimize. And my small f here is just compare the model prediction, how close it is to the actual label, and then I'm just going to sum over. So already in this picture, you can kind of like see the subtlety, right? You have the nonlinear loss, and then you have data that you sum over. Okay, and here I'm not so sure how you're familiar with Thailand, but hopefully you've seen this mudeng somewhere before. It's all over the internet. But if not, let me just introduce this mudeng to you, and it's optimistic being. So it's love to think that things might actually get better if you have like different setting. So for example, it might say that, yeah, the setting here is different and it's more complicated. Maybe that helps. For example, as someone asked recently, that the data encoding part, could it help somehow, right? And early on in the field, there's some papers that actually kind of like trying to push forward this like notion of like, yeah, you're doing some data encoding, it could actually help you getting rid of BP. What we're gonna say here is that, yeah, it doesn't help. Okay, so the very first thing that you could do is you making this like the linear expectation, which is your model prediction, right? And so basically what the connection that you do here is that the model prediction that you have is just a linear loss in your VQAs, right? And then what we can do in that in this work is we link between your actual QML loss function to the variance of the gradients on the VQA loss, right? Which is the model prediction here. And the way you do it is quite straightforward. You just, you have this one. You just do the gradients of this L of theta, and then you just take the variance over it. Okay, that's gonna be some like inequality. You have to doing a bit of like upper bound inequality manipulation, but in the end you reaching like some kind of like this equation, right? And what this equation telling you is quite cool. It's telling you that if you have the variance of your gradients on your VQA loss, if this term vanish exponentially, right, you're going to have the vanishing of your QML loss as well, right? In other words, whatever could cause BP in your VQA is going to cause BP in your QML as well. Okay, that's the first cool stuff that we have. The second one is when we talk about like whether this data is going to help, and intuitively why it doesn't help is because of this, like, you know, you have some initial state. Whenever you do some data encoding on top of it, it's actually going to result into another quantum state, right? So what actually happened is you have some quantum state, and then you still have this parameterized quantum circuit. So, you know, it's just basically you changing your initial state. And if the BP arises due to your architecture of your parameterized circuit, this will not help you in general. Okay. Even worse, right? Even worse, what you could have is like your parameterized quantum circuit doesn't have any BP. But because when you do this data encoding, right, for example, you might encode your data leading to the quantum state that has too much entanglement. And then you're going to suffer from BP, but this time is due to your data encoding part. So we have this concept of data induced concentration in this work. And yeah, so that's basically the first part of the second part of the talk. And then you move, so you can keep playing this game, right? You can keep playing like, okay, what about other different QML models, like generative model that is very popular. So you have like a, you know, image
Sorry, can I make a
generation.
super stupid question before?
Yeah.
You upper bound the variance of the I guess the most general, this one, yes, the cost one by the maximum of the individual, like the local terms or whatever. But there is this number of training data, and I mean, I guess there is it's super obvious that not, but I mean, if you have exponentially many data points, then in principle this scaling could be sorted out.
Sure, you it's going to be loose in that case, but how you're going to like handle exponentially many training data point in practice, right?
Yeah, sure.
So just like so we working under that assumption. We actually had this discussion quite a few times, but in the end we were like, yeah, if you're working with like 100 qubits and people could handle like 2 to the 100 training data points, then that would be great, but I don't think that's happening. So we just like, in data is going to be polynomial. But very nice question. And then you can, as I said, we can keep playing this game. The next one is going to be generative models. And so the actual quantum generative model that we take a look is this like QCBM, quantum circuit bond machine. And the key ingredient here is that it's very easy to sample from, right? So quantum state, if you want to sample from quantum states, aka you want to make some measurement, you just like do measurement and then you have some outcome, right? And then if you want to sample again, you just like rerun your circuit, you make the measurement, you have another sample, right? So quantum model is very natural to sample from. That's what I'm saying. And so the idea of quantum circuit bond machine is like, you just parameterize your u of zeta, and that is going to as a consequence, that is going to parameterize your model distribution, right? Because if you look at what is the probability of you getting this like a x bit string, is going to be in this form, and you're gonna see that it depends on your u of zeta. Okay, cool. Then basically, you can train your model. Here we are looking to train the underlying distribution by tuning the parameters, right? And then you get, you can make sample once you finish training. Okay, it's the same game. Things are different. Maybe it works here because here when okay, so in iterative model, usually you have some sample to train, and it doesn't look so obvious that we are doing some expectation here. So it might work. And just one thing to be clear, that you don't do the data encoding here, right? Just have this view of theta and then just make some measurement. Okay, so a little bit more on how you like to get a bit of idea how you actually train the thing is usually in iterative model, you have some training samples that you have. And then from this training sample, you can construct some like histogram out of it. You're going to do the same thing for your quantum model. You're gonna take some sample, you're gonna construct some histogram. Then you're going to just like compare how close the two are, right? You're gonna compare like how tall is this one compared to the same one with like same bit string, and then so on. So initially, things going to, because like you just initialize your quantum circuit, your underlying probability is going to be like somewhat random. And then once you start training, you keep repeating this process of like you sample a new one, you compare them, you change some parameter, you sample again, you compare new one, you change parameter. Then the overlap of your model distribution hopefully going to be close enough to your target distribution. Okay, and for this model, at the beginning, it's not so obvious at all how we can actually apply the knowledge we have for VQA about BP to this one. But like the two main players that actually help us working this one out is that if you look at the model probability, right, it's actually in the same form as the VQA, in the sense that you can look at this overlap to the X at just like is the expectation value with respect to this like X projector. Okay, and it's going to be the same as your VQA, right? So what we're saying here is that the model probability is going to concentrate under the same condition as the VQAs. And another one is you could look when I say that, okay, you compare your training distribution, training histogram with your model distribution that you have from sample, right? It requires that the two have to be overlapped somehow, right? So that there's some, I can tell that, okay, maybe you tune that one up a bit, maybe you turn this one down a bit, but you have to somehow make a comparison. And what happened in this one is we look at many different losses that people use in the iterative modeling. One big family that we look at is this like what we call like explicit losses, and this is going to include like many loss functions that may look familiar to you guys, like KL divergence, right? Again, the key here is that you need to compare like your training distribution with your model distribution, right? And then you could have like a reverse KL divergence where you have Jensen-Shannon divergence, or even like total variational distance. But like it always like you could always written in this like explicit form. You compare your training distribution with your model distribution, and you sum over your your data. Then what we can show is that under the presence of concentration, the probability of you measuring the 2-bit string, like the bit string that is going to be in your training data set, basically that's going to be like some q of x theta to be the same as p to the x for the same x, this probability actually vanish exponentially under this like exponential concentration. Okay, so what you end up happening is like have like two training distribution and you have like model distribution that you never have any overlap, right? Okay, and that how we actually show it. Some keen like audience might ask like, okay, why can't we just use the result from what we developed previously? And the reason behind this one thing is like the sum here is actually over all the possible outcomes. So it's in the case of bit string, it's actually 2 to the n, right? So this going back to what Matthias asked before that, okay, if my n train is actually exponentially large, then the upper bound become loose. And actually that's what you see here, right? It's not physically, it might be the same, but it might not be the same, but like mathematically behind it is the same in the sense that here I have this the sum over exponentially many terms, and the bound that I have before just loose.
Sorry,
yes.
I don't understand something. Isn't there any way to train in the typical subspace of the like this probability distribution?
Okay, so here is like we work everything under the assumption that you're going to do this like random initialization. Okay, meaning that I have the circuit, then I'm just gonna randomly pick my parameters as like initial parameter for training, and we want to see what would be the consequence under this assumption. And of course, if I have some way, any way of initialize that my model distribution being like a sub, already the subspace of model prediction distribution is have some overlap with the training, you might actually be able to train something, right? We tried that a bit. Actually, it doesn't very obvious to us how we can frame things more rigorously, except that you might actually be able to do some training at the beginning. Okay, and I hope that answered your question.
Yes.
Yeah. Okay. You might also ask, is that everything about quantum generative models? Actually, I skipped like quite a lot in that paper due to the time constraint. But no, that's like the paper is actually quite packed. And if you want to do some quantum generative models, and if you want to do anything in the direction of quantum generative models, I really encourage you to like take a look, even just like diagonally. And it's I'm a good teacher, so I left that as an exercise for the audience. And so sorry for like a follow-up lame joke on this. Okay, so yeah, we coming to the last part of the talk. How am I doing with the time? Okay, it's not so bad, but feel free to let me stop talking at any time. I think it's almost like 1 hour now. Otherwise, I'm just gonna keep going for a bit.
Maybe before, if you don't mind, before jumping into the last part, there is a whole subgroup of ours working on quantum generative models, and super from the it's a bit from the perspective of a applied computer scientist, that now there is like all this boom in these diffusion models and these versions of like generating images and everything. And it's the philosophy which of a lot of some part of the community in quantum machine learning, maybe not coming from the theoretical side, is that of finding quantum analogs of these quantum generative of these classical generative models, like quantum diffusion models or quantum GANs to generate images.
Yeah.
On these approaches that maybe like my question is this one. Should we, should we be careless about theoretical guarantees about trainability in these scenarios or not? Like,
What do you mean by careless about it?
Like, there is this distinction that some people make. For instance, we had Joseph Bowles from Xanadu a couple of weeks ago talking with us, and he was encouraging a lot, like, okay, yes, there is like a lot of trainability non-go theorems about like these variational circuits, etc.
Yeah.
But
Yeah.
for a lot of people, this prevent people to just try stuff. And then, like, the question arises in which, like, where is like this frontier in generative modeling, in which, like, how can we compensate between like non-trainability guarantees and practical things that may work?
Yeah. Okay.
It's a very weird
like,
question, I know, eh?
No. I think that's a very good question. I think like that, and I think what I'm about to say is also like applies more generally beyond the generative model as well, in the sense that I agree with like the Joseph that there are a lot of like no-go theorems out there, but usually like no-go theorems, they work under some assumptions, right? So for example, the assumption that I'm been making here is that we're doing things like quite randomly, in the sense that you do this like a random initialization over the entire like your loss landscape. Again, in practice for like a actual classical machine learning people, they don't do that. So I still think that like empirical study, like numerical study of QML models, they are still like very valuable, right? But what you might want to do is like you're trying to find, you want to be like in the regime that the no-go they don't apply, right? So for example, just before now that you mentioned that, okay, but if I, there's no overlap between training and model distribution, but if I just like find somehow to initialize my model such that there's gonna be some overlap, right, from the get-go, then that is a very good starting point, in my opinion. How it's gonna work out, I don't know. Like theoretically, I don't know. Like heuristically, empirically, I think it's very interesting. Yeah. So basically,
That's a great answer. Yes.
Yeah. So I think like don't be too afraid of like no-go result. But understand them, like in which regime things become bad, and like these no-goes that work under that regime because of like they work under that regime. If you can change that a bit, just being outside of that regime, then you should be fine. But like you also mentioned like quantum QCAN as well. That's also just like some people looking into this like QCANs for the no-go result, like Krista Sufa from IBM. So maybe you can like take a look quickly at like what she's working on. But the same principle applies. It's like, every no-go has some limitation. Yeah. Okay.
Nice.
And then like the last one is what happens if you don't actually parameterize your model. What I mean by here is like in the quantum circuit, or like it's like your parameterized circuit is not actually there. So there are example of this kind of model, like the classic example is the kernel methods, right? In the kernel methods, what you do is like you actually have like quantum kernel. So what you actually do here is you have some input x, then again this is associated to your raw x, And the quantum kernel is the similarity measure between your two quantum states, right? And in kernel methods, you only evaluate these overlaps using quantum computers. And when you actually train things, you do it like classically. There are many good things about kernels. One of them is that under like a mild assumption, your Lord landscape is generally convex, and the base train model, which is guaranteed here, is by base here I mean like the model is guaranteed to minimize your empirical loss. And the way you get that model is just like if you have this gram matrix, right? Which is just kernels over all possible training data pairs. Then you are guaranteed when you do the actual training, you are guaranteed to find the global minimum, right? So for example, if I have like if I do like binary classification with a hinge loss function, that if you write down the step, that is going to like you going to minimize this loss function, and you can see that all the matter is like the stuff that really matters here is just this like gram matrix Kij. And the principle here is that you estimate your gram matrix on your quantum computers, and once you have that, you can just like throw away your quantum computers, and the rest is done classically, right? Okay, I should also mention that this is not the only non-parameterized quantum models. There are like, for example, like extreme learning or like quantum reservoir computing. They work, but all of them work like similarly in the sense that you actually just measure something from your quantum computers, usually some expectation values, and then you construct your model, and then you train them like classically. So people like a few years ago, people like quite excited about this, and they say like, yeah, this is everything, then there's no go result under these models. And what we coming and say like, and then people hate us is no don't be super like ignorant about it. Have concentration on the input space. The definition is almost the same. It's actually the same with the barren plateau definition. You just replace your zeta with your input data. And what it's saying here is that if you have the if you are in this regime, your kernel value is going to concentrate to some point with probability very closely to 1. So I think it's gonna be like quite a bit to go. I'm going to be very quick, but like the summary is the following. For the source of the concentration, right? Because if you look at the form, it's actually the same as your barren plateau definition. So whatever could cause BP is going to cause your this like concentration over the input data as well. And again, it's all about curse of dimensionality. The very interesting part is the consequence of it, right? Because as I said before, you are guaranteed to get the best train model. So then what concentration actually affects you here, right? So what we found, which is very cool, is that you're going to get the best train model, given that you have some gram matrix. And what we show is that when you estimate your gram matrix under this concentration assumption, your gram matrix, your estimate of your gram matrix is going to be insensitive to data. And then when you do all the training, you're going to have the data insensitive model. And it's like if you do machine learning and your data, your model does not respond well to the data, then you know that it's not a very good thing to have. And the way you can think about this one is because the precision is very costly in quantum computers. Sure, the kernel is the only thing that you want to estimate here, but you still have to estimate with some measurement shots, right? So for example, if you look at this like fidelity quantum kernels, then you want to estimate this kernel, you're gonna have to do some measurement. And the estimate of your kernel is going to be like in this form, right? You sum over the lambda I, where lambda I is the outcome of your I measurement divided by the total number of measurements you have. And you could do this with like swap test. So for example, if you run the circuit below, you are guaranteed that when you measure the expectation C on your ancilla qubit, is going to be your kernel value. So in this swap test, you can work the math out. What happened is that you're going to have the output to be +1 with probability half plus your kernel value divided by 2 is going to be -1 with probability half minus k divided by 2. When you have concentration, what you actually end up is these kernel values, they are going to be exponentially small with the probability exponentially close to 1. So basically they are very small. And if you compare the outcome according to this kernel distribution to the some data independent uniform distribution, which is just like 1/2 here and 1/2 here. And this thing, you can treat them as like some exponentially small perturbation. What actually happened is that you cannot really distinguish whether the sample are coming from the uniform distribution or the kernel distribution, right? You cannot decide. So what we actually doing here is we just put things into more like a rigorous footing. You're using like tools from like hypothesis testing, and what you can show is like so the game here is that you have some sample coming from the kernel or the uniform, and then the agent has to make the decision, right, whether it's from the kernel or the uniform. And what we show is that the probability of the agent to make the correct decision is very close to 50%. So that's just random guessing. And so we have this presence of concentration cause you the statistical indistinguishability in your models.
Sorry, Supanut.
So, yep.
In this paper, do you, because you say you have ensamples?
Yep.
Those ensamples are used to estimate the kernel, or are like n experiments in which you have estimated the kernel already? No. Okay, you used it to estimate the kernel.
Yeah, and then when you have like another pair of kernel, you just like doing like another n samples.
So there are like no rates involved when you talk about hypothesis testing.
There's no what involved, sorry?
Rates, like rates in which like the error rate decreases, whatever. Like you're playing like to distinguish between the uniform distribution and the uniform plus epsilon minus epsilon.
Oh no. Here like you talking about the tolerance of acceptance, or so here so what actually happened here is like, so the assumption here is actually in favor of being able to distinguish. So we actually assume that you already know the kernel distribution, which in practice you don't, and you have the the uniform distribution, and then you just have to make the decision between the two. And what happened is like, so mathematically what happened is that the probability of you making the right distribution is like 1/2 plus some correction term, where the correction term is vanishing exponentially. So it's like you have the factor of like 1/2 to the n, something like that.
Okay.
Yeah.
Cool.
And of course there's like the sample, there's sample factor in that correction term. But again, here we're making assumption that everything is polynomial. So basically, you cannot make 2 to the 100 measurement shots. That's what we're saying. Okay, so what we have here is just that you have, because your estimated kernel values are independent of input data, and then you just have data in sensitive model. Okay, you could ask a bit about, so by that it's just bad generalization, right? You have a new unseen data, you cannot make the right decision. It's random case basically. You can ask a bit further, like what actually happened to the trainability, and then also like whether this bad generalization is the same as like bad generalization that people usually observe in classical machine learning. And what we see here is that it's kind of like a new favor of bad generalization, in the sense that, okay, in the classical machine learning, when you have bad generalization, you actually be able to have like a more and more accurate, like a better performance by having more training data, right? What we show here is that it's no, it's like what we do here is we cook up some like some engineer example to specifically show this phenomena, in the sense that this line is the line that you can perfectly estimate your kernel. So you know the kernel values exactly, and it's under this exponential concentration. So in this example, if you know the kernel value exactly, even with exponential concentration, you can actually improve your error, right? You can actually improve your generalization. It's going down, but this is only when you know the kernel value exactly. What we show is that if you estimate the kernel values with your polynomial measurement shots, things are bad, right? You don't get any improvement even you even you increase the training data. Okay, so it's a new favor of generalization. Okay, so that the summary of what I just said. I want to also emphasize again that this phenomena is not happening only in the kernel methods. Other parameterized circuit also having this, like extreme learning or like reservoir computing. Okay, now probably come to the most important takeaway messages, right? Okay, so the first thing that I want to emphasize is that the concentration, if you just keep looking at what I've been showing you so far, exponential concentration, there are arises from people being, I don't want to say optimistic, but being like ignorant, right? So people, if you think that that's going to be like one quantum machine learning model that gonna work for everything, it's gonna always outperform classical machine learning, then that's probably not the right mindset to have. Okay, and the second one is whether your model is going to suffer from concentration or not. You have to think carefully about what you actually measure in practice from to construct your model from quantum computers, right? And if the quantities that you want to measure, they suffer from concentration, then that's probably not a good sign. And the next one is concentration is everywhere, but not everything. You also have other problems, other challenges like local minimum, like what is the good learning problems. But I don't want to. So I don't want to actually discourage anyone here, because actually like there's some hope in quantum machine learning, right? So there are people showing that if you think carefully about like what problem you want to solve with quantum machine learning, you can actually have the rigorous guarantee on your quantum advantage, right? Yeah, so I think that, so Okay, these are my lovely and amazing collaborators. You know, it's like Marco and Zoe, and like a lot of good PhD students from EPFL. You know, master student, Tip from here, like Samsung, who's now in Caltech. And yeah, thank you for your attention, and please ask me any questions.
Thank you.
Yeah.
I don't know how to clap virtually, but thanks a lot.
I hope I did a good balance between like telling you what's going on and like some mathematical details.
For I mean, it's super amazing talk. Thanks a lot. Does anyone have any question, thoughts?
Maybe I can have a question regarding the last part that you were mentioning that you are preparing a new manuscript on the reservoir computing. Could you give us a little teaser of what is it is going to be about? What is what are you investigating in this specific and why are you focusing now on this instead of choosing other potential lines of research? Because I think that you understand that that this is one interesting place to learn things. We have been discussing internally in the group also about the role of reservoir computing, and I think it's a super interesting topic to talk about.
Yeah. So I think this one is just like a natural follow-up from our quantum extreme learning work, because in quantum extreme learning, it's just like you can think of it as just one layer of the reservoir computing, and the quantum extreme learning we got this just from like, you know, this in under similar family as the kernel methods. And because like we have some master students and we have to find some project for them to work on. But yeah, it's just going to be like, so for extreme learning, things are very similar to what you have in kernel, right? Because what people usually use for extreme learning and kernels, they are going to do like regression and classification. So things are pretty much like very similar. For reservoir computing, a bit more tricky, because now what you actually do is just like a time series prediction. So you have like many layers, and you input your data at like a different points in time before you actually making some prediction. So the key here is like, so okay, let me talk about the cool stuff first. What we have for the cool stuff is, I'm not so sure if it's cool for community, but it's like I'm very excited about it. Is that in these two frameworks you employ what people call like a reservoir. It's just some fixed unitary basically to just kind of like mix things up. And what we found here is like it's simply another source of concentration if you have the reservoir that being too random. And this kind of also like partially going against what people in the classical ML community have, that when people doing this kind of like a reservoir computing, people kind of like, yeah, you want to have your reservoir to have a lot of randomness. What we say here is that like in quantum, too much randomness is not good. Yeah, so in reservoir computing, it's just gonna be the same as in the extreme learning, but the math here is a lot harder. It's like surprisingly a lot harder, because like here you have to, if you do like a t time step, you're repeating your UR like t times, but it's the same UR. And when you write the math out, you cannot just simply apply like the hard integration that you usually just like use whenever you want to do this kind of calculation anymore. Yeah. So that the geek side, right, is the like the math side, the fun side that I'm fascinated. But like practically, I feel like the concentration is going to affect less for the reservoir. because usually people like don't. So this U is kind of like fixed. Your reservoir is kind of fixed, and in general, people just like apply some like a physical dynamics to it. Just like you have some physical system and you evolve it for like some time, and people use that as reservoir. And to us, it doesn't seem very clear whether that could cause concentration or not at this stage. And there's some people finding some empirical evidence that it might not cause the things. So, maybe it's not that bad. Yeah. Did I just bored people with like a very long speech of how I love to do maths? But
No,
yeah.
It's
but
I have a few comments, but I feel it's amazing, like how like how much developed the study of VPs concentrations is at this point. But it's also true, like what you pointed out, that it's not the only caveat in machine learning models, no?
No, definitely.
But I guess it's one of the I mean, it's not easy at all, and it's like for us in like the computer vision center is kind of a wall that we cannot penetrate. But because her measures, etc.
Yeah. So maybe like one criticism that like I always get asked, and maybe like it's good point to bring this up just to give people like a bit like a bigger picture understanding, is like part of the reason I'm working on this one is it's just one of the areas that you can actually do things rigorously, right?
Mm-hmm.
And so sometimes people criticize it about being like, yeah, it's just like, specific regime that you can do some maths. Of course, it's nice, it's beautiful, it's some no-code theorem, but like how it's gonna, so sometimes people don't really believe that this kind of thing can actually hinder your scalability. I would say that that's kind of like partially right, in the sense that if you are very careful about what you do, like you think very carefully about like each step that you do, run your like about the simulation that you want to set up to run on your computers, then in general, I don't expect the no-code result to kick in. But this no-code result usually coming from like you being like super ignorant and just like, yeah, I'm just gonna try and see if this works. And it's like it might actually work for like a few qubits, but then if you're not super careful, then when you scale up, it does not work anymore. Sometimes I feel like I discourage people to explore things more, but I don't think that's my intention. I think my intention is just like, yeah, people have to think a bit more carefully when they want to explore stuff. I actually believe that there's some some good opportunity to explore in QML. For example, like this paper that people actually show that you have some advantage, right? Is very nice paper. People show that if you encode like Shaw algorithm to solve the learning problem, that the underlying hardness is about like doing this like discrete log problem, which is just log version of prime factorized. Then you can actually show speed up, and it's rigorous. I like that. And all these like theoretical results, they're gonna be around for a bit. I think I'm gonna keep doing that because it's cool. But at some point, when we have like large quantum computers, I really expect things to play out exactly as the classical machine learning community, right? It's just you're gonna have to be able to run a lot of like empirical studies. There's gonna be a lot of results that you cannot explain with like the current theoretical understanding, and I'm really looking forward to that.
Cool.